Hello, I'm Mr. McBrien. This is TEJ20, Integrated Circuits. So integrated circuits, also known as chips, we're going to talk about what's inside them from several different perspectives today. So when we're finished, we're going to be able to describe chips from several different angles and really, without any more explanation, let's just start in. So, an integrated circuit, essentially we can view it as a collection of transistors, and those transistors get arranged together to form the logic gates that we've talked about previously. When we combine those logic gates together in a logical way, then we have ourselves a circuit. When we put a circuit for a specific purpose onto a single device, then we have an integrated circuit. Okay, so that deserves a lot more unpacking, of course. But hey, let's just start talking about the underlying technology, what they're made of. So the chips are essentially formed from silicon dioxide. So we can say in many ways, chips are made of sand. So we can't make them simply out of the sand we find at the beach. We have to purify it greatly. As a matter of fact, there's an entire science around the purification of silicon dioxide into extremely pure materials that we can then use to make into the chips we've talked about. And once we've done that, on that substrate, on that material, we can transfer across a large amount of very small transistors. And this process called photolithography puts lots of transistors into a very small space, and this can be done reproducibly, mass-produced. Now the result is densely packed gates on a given chip. Now in some cases we don't have that many gates on a chip, but in other cases we want them as closely packed together as we can get them, making this extremely small, extremely fast processor. So Texas Instruments, for example, can put 180,000 transistors on the surface area of a human hair cross-section. That, of course, is extremely densely packed decision-making power. Now, if we want to talk about how we use that power, we can then dig deeper into this idea of transistors and gates. So on the top, on this slide, we have a microscope picture of a gate on a 555 timer. And then underneath, we have a look at the given materials that are used to create that gate, what was deposited on top of that substrate that we talked about in the previous slide. So the CEB is no coincidence, right? So in our transistors, we talked about collector, emitter, and base. And in fact, that transistor has been put in microscopic form down onto this chip. So we can view the chips, and this is our first look at a real one here. We can view these chips in terms of the decision making that they do. So we're back to our logic gate picture. So this integrated circuit contains 4 NAND gates, which are created by 8 transistors in a single 1 centimeter long package. So we can view it from the logic gate point of view. Notice we have 14 inputs and outputs here, and 14 pins on our chip. Here's another example of 4-bit adder circuit. Notice the packaging looks almost exactly the same, and we'll talk in a few seconds about why that packaging is standardized. We have a different kind of view of this adder circuit here in terms of its logic. Another familiar integrated circuit, the arithmetic logic circuit, is shown here from a flowchart point of view, and this integrates together adders like the one we saw in the previous slide and other gates to create a mathematical engine that we talked about back in the first unit. In addition to that flowchart view, we can also, here's a subset of the gate view of that ALU. So you can see this is an extremely complicated chip, and remember, this is only a part of that chip. But these gates go right back to looking at what we studied in the previous day or two. Okay, if we want to go all the way up to a CPU, which is just another integrated circuit, albeit a very large and complicated one, we can't even pretend to look at the individual logic gates involved, and we can only take this flowchart view to how a CPU works. It has our arithmetic logic unit integrated in it, as well as an interface to memory, etc. And unpacking that further, we can talk about why we could never look at the individual numbers of gates. The i7 chip, Intel doesn't publish anymore how many transistors are on it, but we can project that it has right around 2 billion transistors in it. A very, very complicated integrated circuit. On the other hand, not all ICs are complicated at all. So this is a 555 timer chip, and it really just has a couple of simple switches and a voltage comparison device. And we'll talk a lot more about this tomorrow, this simple, extremely useful chip. In fact, this is the, since its inception around 1974, it's the most produced integrated circuit of all time. On the other hand, some integrated circuits are just for fun. So instead of a timer, this UM66 chip is called a melody chip because it changes its output at a frequency that matches sound. So if you've ever given anyone a musical birthday card, it will have contained a UM66 integrated circuit. Another interesting integrated circuit, the 4017, counts to 10, and that's its real purpose, is just to count to 10. Now, why is this useful? Because combined with an appropriate timing device, it can actually form a clock. So it has a great deal of usage in various devices. So how do you know how to use these things? How do you know which pins to attach where? How do you know how much power to put in? Well, the answer is the same as it's been for any other component in our course. Virtually all electronic components have an owner's manual online that describes the inputs and outputs and pin functions and things. Anytime we want to use an integrated circuit, we should retrieve the datasheet online. Now, when we go to use that circuit, there are a couple little rules of thumb that will help us to avoid burning them out and help us to avoid breaking them. So if you need to solder your integrated circuits, don't solder them at all. So what you do is you solder down one of these handy sockets These pins can handle heat without getting damaged, but also if your integrated circuit wears out at any point, you'll notice that these spring clips hold in the actual chip. Well, you can swap out the chip without having to replace the entire device. In a breadboard, you can simply insert the integrated circuit directly onto the breadboard. And what you do is, this is what the purpose is of this split across the center of the breadboard. And then if you use that location, slide that integrated circuit into place there. Each of the individual pins, you have four ways to connect to each of the individual pins on your integrated circuit. You can go ahead and do that very simply. Now, when you go to place the chip on the board, there's something you need to keep in mind. These pins are extremely delicate, and you need to make sure that every pin has seated itself into the hole on the breadboard before you start pushing. And if you don't do that, you're going to wind up with bent pins, and bent pins very quickly become broken pins. So if you're finding yourself pushing very hard on the integrated circuit, trying to get it into the breadboard, what you want to do is look for an individual pin that isn't seated properly. And it may need to be bent slightly to make it touch the hole at the right angle. Okay, that's our quick run through integrated circuits. So our take-home message from this: integrated circuits package together several transistors into gates that interact to give us some kind of a logic, a functionality specific to that chip. These can become part of an overall circuit, part of a device, and can be configured in various ways depending on the components they're combined with. Some integrated circuits are extremely complicated with billions of transistors. Other ones may contain as few as 8 or 10. If we want to understand the function of an integrated circuit, we consult the online datasheet and go through that to figure out how to use it effectively. Thanks very much. Have a wonderful night.